Hi everyone, my name is Yasid Jayakodi and welcome to the first tutorial of our YouTube series Surface Design. If you had missed the introductory video, I recommend you have a look at that because I have discussed the importance of surface design engineering and what a surface design engineer would expect once you go into the industry. I have also briefed about the advantages of having a surface design engineer in your team. And as I promised in that video, I will be going through surface design engineering step by step, starting from the most basic models and going to the complex models, which needs a little bit of expertise if you are starting from the beginning. In this tutorial, students with no experience or lack of experience in the subject will be able to follow with me, and hopefully by the end of the series, you will be experts as well. Before we dive deep into our tutorial, I would like to give you a small introduction to the session. If you look at your right hand side, we have a Bloom's taxonomy pyramid. And this is a learning model that lecturers use to make sure that the design or the flow is smooth. I would like to make some changes because of the nature of our lecture, and also because we are going from the very beginning. So what I will be doing is, without bombarding you with the theoretical knowledge, I will first like to show you two of the most basic surface reconstruction techniques, build a model from the two techniques, and in the end, you will be analyzing these techniques using the most basic forms of analytical methods. In this case, we call it the visual inspection. And hopefully we'll be able to have a good discussion on which method is best and which method you can use for models. To start with, I decided to incorporate an extremely simple model, something that we all have used. A simple cup. Cups can come in different shapes and sizes. To initiate the reverse engineering process, we should build up on dimensions. Imagine this was a very complex object. It would be impossible to go ahead and dimension it with a vernier caliper and a micrometer screw gauge or any other manual technique. Therefore, we have something called the laser scanner. Now, if you're interested about the laser scanner, I recommend you look at my other video where I have detailed its steps and procedures. At the end of the laser scanning process, we should have something called a point of clouds. These points define the surface. Now, in theory, all these points should live on the surface of the object, giving us an accurate representation of its surface. However, in reality, it's not so sweet. What you would expect are a majority of the points living on the surface of the object, but some of the points can be a little offsetted beneath the surface. We call this offsetted points and subsurface points, respectively. You can import the cloud of points to Siemens NX by clicking File and going to the Export option, and make sure that you select the point of clouds. Normally the point of clouds is a .pts file. So I will orient my model in the Z x-axis, and I will hide some points to avoid the confusion. And make sure you hide the points and don't delete them by clicking the Ctrl B shortcut. I'm going to use the Fit Curve option and make sure I select the Fit Circle option from the drop-down menu and define some points in the circumference of the circle. I recommend you use the Fit Circle option compared to the Studio Spline option, because it will give you an accurate circle. Most of the time, your datum coordinate, if you're lucky, will be in the center of the circle, but if it's not, don't worry about it. So as you can see, the datum point and the center of my circle are two different points. Now, because the circle that I create is angled, what I'm going to do is I'm going to create another sketch, and I'm going to project the curve onto my plane using the project curve function. I'm going to create a plane that cuts my datum point. Therefore, I'm going to click the datum plane, and from the drop down menu I select the point and direction option. Make sure I select the point, and you can include whatever direction to draw a line perpendicular to the direction of the circle that you just drew, like this. We'll be using this line later on when we are defining the other circles. For now, I'm just going to hide the line. I'm going to create another plane that intersects from a random point, but make sure that the plane is facing at the same direction. And I'm going to hide some points that I think is not needed. And use the fit circle option to draw another ring. And I'm going to repeat the process until I am satisfied with some layers. To save time, what I'm going to do is I'm going to hide some of the points and color the remaining strips of points. And when I'm repeating the process, I only select the red dots, which correspond to the different levels. We have made the rings using the fit curve option. And now it's time to check whether the center points of these rings are vertically above each other. So if you look at it from the top view, you can actually see that it has a slight offset. I'm going to create some circles, but before I delete the circles that I just made, I'm going to take note of the radius. You wouldn't be able to do this step if you made splines, because splines can have different radius, depends on the location. So to measure the radius, I go to the analysis option and select the measure. and I'm going to select whatever plane that I want. Make sure that you select the radial option and define the radius that you made note of. And what I immediately do is hide the curve that I don't want and color the curve that I just drew. You can use the through curves option to join curves to curves and also curves to points. In this model, you can use the through curves option and guide all the 6 curves and end the model by selecting the last point. However, I want to show you some other techniques which will be beneficial. Therefore, I'm going to leave my model unfinished and not select the point. So it will be a hollow object like so. Now, as I told you, you can use the through curve option to connect the last curve to the center of origin. But I want to show you some other techniques. You can use the fit surface method. Now, what a fit surface is that it tries to fit or create a surface to fit the set number of points. And you can play around with the degrees of freedom in the U and V directions, which means in the X and Y directions. Also, I want you to notice that when I increase the degrees of freedom, the minimum error or the average error decreases. What it tries to do is it tries to make sure that the surface cuts through all the points, therefore making the surface more accurate. But in reality, since the points are scattered and not in a 2D plane, we don't want this because we don't want our surface to be warped. We want a smooth surface. This is something that you can include in your report. In my case, fit surface will not work. Therefore, I will have to improvise. What I'm going to do is create a spline and revolve it. I'm going to make sure that the starting point of my spline is the origin of the perpendicular line that I drew, because it is going to be the point of rotation. And I'm going to make sure that the spline does not extend all the way towards my surface, because I want to show you the capabilities of the through curve function. Please make note that I have the through points command. What it means is that, as the name suggests, the studio spline that I'm going to create will intersect all the points that I define. This does not give me adequate local control. But we are going to go with it anyways. And I'm going to show you another technique that you can use later on, where you'll be able to use the same studio spline command effectively. Great. So now I'm going to use the through curves option, and I'm going to bridge the two surfaces. When we are bridging, we would like to have G2 or G3 curvatures. However, because of the shape of the model, this is not always possible. And if we try to force the software to do it, it will give me undesired results, just like this odd shape right here. Now, I don't want that bump in the end. Therefore, I'm going to compromise and set one of the surfaces to G1. The next technique that I'm going to show you requires less time. And this is called the revolved option. I'm going to orient my model in the top and the sideways to delete the points that I don't want in order to get a quarter of the profile, make the process so much easier. I'm going to join the points in the same way that I did before, using the through points option, but then I'm going to change the criteria to through poles. Without going into the deep mathematics of it, through poles option gives you a better local control compared to the through points option. In surface design, points and poles are geometric terms that are used to describe the behavior and shape of a surface. A point is a location on a surface where the curvature is zero, meaning that the surface is neither concave nor convex at this point. In other words, a point is where a surface is flat or planar. Points can occur on the surface either as isolated or as part of a line or curve. A pole, on the other hand, is a location on a surface where the curvature is infinite, meaning that the surface is very sharply curved at this point. Poles are typically found at the top or bottom of surfaces that have rotational geometry, such as spheres or cylinders. Points and poles are important in surface design because they help the designers to understand and manipulate the shape and behavior of the surface. For example, the presence of points can be used to create flat regions on a surface, where the poles can be used to create regions of high curvature or control the flow of the surface. And that is exactly what we experienced in today's tutorial. In addition, the location and distribution of points and poles can impact the way that the surface reflects light, making them more important consideration in the visual designing of a surface. Overall, points and poles are key geometric concepts in surface design that will help designers to create surfaces that are aesthetically pleasing, functional, and well suited to their intended use. Thank you. What it means is, if you want to make a minor change in a spline without affecting the entire curve, you can do this using the through poles command. And this is what it's called a local control. However, if you want your change to cater a large area, sometimes you want to do that, you can choose the through points option. And these are the differences between the Bezier curves and the B-splines. We'll go through that in detail when we are talking about the theory. But for now, all you have to remember is use the through poles command for a better local control. The bluish model was created through the through curve command, and the grayish model was created through the revolve technique command. And if you look at the side view, specifically if you look at the open end of these two models, I would give points to the model that was created from the revolved function, which is the grayish model, because look at that front lip. However, if we check the reflection analysis, now what we want to see is undisturbed lines. And as you can see in the revolved section, we have a nasty bump, and therefore our reflection analysis is disturbed towards the mid part. However, if I were to judge these two models based solely on the reflection analysis, I would give points to the model created using the through curves method. In conclusion, I would be confident to confirm that a better model could be created using these two techniques at the right areas. For example, I could use the revolve technique towards the open end of my model and use the through curve technique towards the middle and end part. Furthermore, focusing on the through curves technique, I think that we can hit a better accuracy if we had more number of rings.
Reflection analysis is a technique used in surface design to study the behavior of light as it reflects off a surface. This technique involves analyzing the way that the light reacts with different surface textures, finishes, and even colors. Design engineers create visually appealing designs by understanding how the light reflects off different surfaces and what effects it can create by adjusting the different design elements. This can particularly be important in fields such as product design, architecture, automotive design, and even in the aerospace industry, where the appearance of surface can have a significant impact on the user's experience or the product's performance. To perform a reflection analysis, designers may use a range of tools such as computer modeling software, as we did today, physical prototypes, real-world tests using light sources such as lamps or even under the sun. One example that I can think on how reflection analysis is used in the industry is in automotive design. Car manufacturers use reflection analysis to design cars that are not only aesthetically pleasing but also safe and functional. The way that the light reflects off a car's surface can impact its visibility to other drivers as well as the driver's ability to see the road clearly. Car manufacturers use computer modeling softwares and real-world testing to analyze the way that the light reflects off a car's surface from various angles and lighting conditions. This helps them to optimize and design the car's exterior, including the shape, color, finish of the surface, which might affect the adjusting positions and the type of lighting on the car. All of this is done to provide adequate visibility to the drivers and to meet the safety standards. Reflection analysis is also used in design of buildings and furniture. Overall, reflection analysis is critical tool in the surface design engineering tool arsenal. It helps designers and manufacturers to create functional, aesthetically pleasing products that meet the needs of the preferences of the users. So to sum up today's tutorial, you got introduced to the world of surface modeling, developed two models out of two basic techniques, and compared and contrasted the techniques using the most basic type of analysis, which is the reflection analysis, got to know what the reflection analysis is, and hopefully you will use these techniques in the future in my tutorials. Thank you, and I hope to see you in my next video.